Welcome back to Algorithms and Uncertainty. Like last time, also today we are considering a problem of optimal stopping. This means we are presented a number of candidates, and after seeing one of the candidates, we immediately and irrevocably have to decide whether we accept, so for example hire this candidate, or whether we reject them, so they will be gone forever. Mathematically, this means we see this sequence of numbers and we have to stop this sequence at some point. Last time we were assuming that these numbers are drawn from known probability distributions, and these numbers arrive just in some fixed order, so just for what we see in the first step is drawn from the first distribution, what we see in the second step is drawn from the second distribution, and so on. Today, we make a different assumption. We don't assume to know anything about the candidates in advance, so we don't assume to know any probability distributions. But what we assume now is that we know something about the order in which the candidates arrive. Namely, these candidates arrive in a random order. And this helps us in an obvious way, because over time we can see what will good candidates be like. And then depending on what we see throughout the sequence, we can then decide at which point to stop the sequence. So let's first formally write this down. We can think about it this way, that an adversary defines values v1 through vn, which are non-negative, and then a random permutation pi is applied, and by that I mean one of the n factorial permutations is drawn uniformly at random, and we now have an arrival time pi of I for candidate I. And in step t now the following happens. We see candidate inverse of pi of t, and then we have to accept or reject them immediately and irrevocably. And as a simplifying assumption, we say that all these values are distinct. This helps us to state the problem or the algorithms much more easily. And this problem is now called the secretary problem. Yeah, well, the problem that we had last time doesn't have a real name. Sometimes you'll hear this in the context of profit inequalities, the profit model. I call it just the known distribution models. Here, this exact problem is known as the secretary problem, where the early motivation for this problem, the story that people told about this is that you want to hire a secretary and you see these secretaries and you immediately, after having a job interview, have to decide whether you accept or reject this candidate. How can we solve this problem? How can we, first of all, understand this in the context of our general theory that we have so far? Can we represent this as a Markov decision process? Well, it's not obvious. While this problem with the known distributions is pretty obvious how to represent this as a Markov decision process, here this is not possible because there are these values v1 through vn which we do not know beforehand and which are revealed to us only one after the other. And so this is the reason why actually it is not obvious how to capture this as a Markov decision process, because in a Markov decision process, in advance we know everything except for the random outcomes. But fortunately enough, there is a representation of at least a problem variant, which we will be considering in the second part of today's lecture to also get an understanding of this precise problem. But before that, we will simply design a simple algorithm which just uses the fact that we see a random permutation, and then we'll just analyze this simple algorithm before then in the second part, showing that we couldn't actually have done something a lot better than our very simple algorithm. Let's now try to design a very simple algorithm for this problem. So what is happening? We see these candidates in a random order. We don't know anything in advance, so there's not a lot that we can do. But what we cannot do is we can just first have a look at them, at the first ones that we see, and well, we have no choice but to reject them. And then at some point we say, okay, now we have a good understanding of what good candidates must look like. And then we take the first candidate who is actually better than anything that we've seen up to this point. This is a threshold algorithm because there is just this one point in between where we stop or where we switch from observing the candidates to actually accepting the candidates. So formally, we observe the first tau elements of the sequence, and afterwards select a candidate if it is better than anything that we've seen so far, so if it is the best so far. And here it actually turns out to be helpful that we assume that all values are distinct, because now there's no problem with tie breaking. So either it is the best so far or we've seen something better up to this point. It never happens that we see two candidates which are equally good. And for this, we will show the following theorem for this algorithm. We will show that for any tau, the algorithm selects the maximum valued candidate with probability as follows. Take the sum from tau plus 1 to n, and then it is 1 over n times tau over t minus 1. Good. What does this mean? Here this probability is even exactly, so there's not even stating that this probability is at least this much, this probability is even exactly this much. Now the question is, of course, how should we choose the tau? For how long should we be observing the sequence, and when should we actually start accepting candidates? Well, let's see what this should look like for large T, for large N. Sorry, what we'll have is that this sum that we have here this we can actually lower bound by the following integral. Move out t over n, and now take the integral from tau to n of 1 over x dx. And if you now do the math, then you'll see, okay, this is actually equal to tau over n times ln n over tau. So this means that if you now set tau to n over e rounded down, you'll get that this tau over n times ln n over tau, this will be equal to how much? This is at least n over e minus 1 divided by n times ln n over n over e without the minus 1 now. And this is 1 over e minus 1 over n. Which means that for large n we are getting a probability of approximately 1 over e. And if you now realize that large values of n are somehow without loss of generality, because you can always add candidates of negligible values to your sequence, then you'll see, okay, the probability here that you select the best candidate will be like 1 over e. So this means there is an algorithm which selects the best candidate with probability 1 over e. Or let me now write probability at least 1 over e, to be clear that here this probability was exact, here we only have a lower bound on the probability. And this also has a further implication, namely what's now the expected value of the choice of our algorithm, this is something we can lower bound by the maximum value in the sequence times the probability that we select actually the best. And this now will be at least 1 over e times the value of the optimal offline solution. So this gives us some kind of a guarantee which is similar to what we had in competitive analysis, namely that the expected value of our selection is at least a 1 over e fraction of the optimal offline solution. Now there's nothing random about the optimal offline solution because we assume that there's just some adversary who defined the sequence of values, so there's just some fixed value of fixed sequence of values. They are not random variables, but where is this expectation coming from? They are presented to us in random order. So this is not like a randomized online algorithm where actually we were the ones introducing the randomization. The randomization is actually coming from the fact that we have this random order being applied here. Good. So this is, interestingly enough, I think also a way to weaken competitive analysis in a way that you can still get a meaningful result, although with this purely worst case perspective where everything was adversarial, including the order, you couldn't prove anything, or you could only prove trivial things. So what we want to do now is, of course, show this bound. So we want to show that for any tau, the algorithm picks the maximum valued candidate with this probability. How do we do that? Well, we can say that without loss of generality, V1 is bigger than V2 is bigger than, and so on, is bigger than Vn. Why that? Because this sequence is just fixed a priori, but the indices here, they don't mean anything because afterwards this random order is still being applied. So we are not, V1 is not the first one that we're seeing, but we're seeing V1 just at a uniformly random place in our sequence. Same about V2 and so on. So we can now say that the algorithm succeeds, meaning that it picks the best if what happens? If, on the one hand, pi of 1 is greater than tau, which means that the V1 element arrives after tau. Remember that if it arrives before tau, then it will not be picked, so it will have to arrive after tau. And no other element is picked before pi of 1. So what we're interested in is the probability of this event. And this we can now write as follows. We can take the sum from tau plus 1 to n. And we're now interested in the probability pi of 1 is equal to t, and no element is picked before round t. Good. So all we want to do is we want to understand these probabilities, because those we have to add up eventually. Why, by the way? So here this should be, we select the best, of course. Why do we have an equality here? Because those are disjoint events, of course. Here we are determining, we're distinguishing between where the best candidate arrives, and it arrives either in step tau plus 1, tau plus 2, or tau plus 3, and so on. Now how can we understand this probability? We now let ST be the elements that arrive before step t. And no element is picked before t if and only if now this is maybe a little mysterious now how I'm writing this. I'll tell you in a second why this is true. If and only if the position at which the minimum of the ST arrives is at most tau. Let's slow down here. Maybe we should once again convince ourselves why this is true. Well, we select the best candidate if and only if the following happens. The candidate arrives after step tau because, well, if it arrives before step tau, we won't be selecting it. If it arrives after step tau, it will surely also be the best so far. But it may happen that at this point when the best arrives, we have already stopped the sequence. So we have to have that no other element is picked before this step when the best candidate arrives. Now we decompose this into these disjoint events, depending on where the best candidate arrives. And now we introduce some notation, namely ST is the set of elements or the set of candidates that arrive before step t. And now we want to say, what is this event that no other element is picked before pi of 1? Well, this means exactly that the best of the candidates that arrive before time t arrives until time tau. Because if this is true, then no other candidate arriving between tau and t will be accepted because there was something better. On the other hand, if the best one arrives between tau and the best so far arrives between tau and t, then it is selected there, of course. So this is why the event that no element is picked before t is exactly what I was saying. Now this is maybe a strange way of writing this, but it is the most convenient way now. What's the minimum of the ST? Well, recall that we ordered our candidates so that the ones with a smaller index are actually better. So the minimum of the of the set ST, this is the index of the best candidate within ST. And so what we'll need is exactly that the point at which it arrives is at or before tau, because only after tau we start accepting. Good. Now, how can we understand this probability here? The probability of selecting the best is equal to, take the sum from tau plus 1 to n, and now what is the probability that pi of 1 is equal to t, and that the pi of the minimum of the ST is at most tau, or how can we rewrite this? Is the probability that pi of 1 is equal to t times the probability that pi of the minimum of ST is at most tau, given that pi of 1 is equal to t. So, what are these probabilities? Well, this first probability, this is somehow easy to state, because this is just asking what is the probability that some candidate, in this case candidate 1, arrives at a certain time. And when we're taking a uniform order, each candidate is equally likely to arrive in each step. So we have n steps in total, so this probability will be 1 over n. But how big is this probability? Well, there's something annoying here because we have now this conditional probability. We are now conditioning on one candidate arriving in a certain step. But fortunately enough, this is not super difficult to understand, because here we're just talking about who arrived before time t. Who arrived before time t and what was their order. Well, if we now have a closer look at this, then we see before time t, we just see a uniformly random subset of all the n-1 candidates. So there are like this one candidate is fixed to arrive in step t. The other candidates, the other n-1 candidates out of these t-1 will arrive before time t, and this set, of course, will be just a uniformly drawn subset of these. And then we have one minimum of these, and this minimum then has to arrive until time tau. This is why this probability will be equal to tau over t-1. But I guess we should go a little more have a closer look at this in a little more detail, why exactly this is the probability is this much. So what is the probability that the minimum of ST is smaller than pi of the minimum of the ST is smaller than tau, conditional on pi of 1 being equal to t? Well, now let's write this down really formally. We're now drawing a set M, which will have to be a subset of 2 to the m. And now we're interested in what is the probability that St is equal to m and pi of the minimum of m is at most tau. And then we're conditioning on pi of 1 is equal to t. So here we are actually saying that m is only a subset of 2 up to n because 1 cannot be included in the set St. St, recall, is everybody who arrives before time t, and we're conditioning on 1 arriving at time t. So this is why we only take a subset of 2 up to n. And now, what's the amazing thing? Well, let's again split up these two events into two separate points. Namely, what has to happen? Well, first of all, the set of candidates arriving by time t has to be m, and don't forget that we're still in the conditional probability space that pi of 1 has to be equal to t. And then what still has to happen is that the minimum of m has to arrive before or at tau, and we're now conditioning on St being equal to m and pi of 1 being equal to t. Now, what is this second probability? We're now just fixing t minus 1 candidates to arrive by time t, and out of these we'll have said nothing about their order so far. And this is why we, as I was claiming, have a probability of t over t minus 1 that the one candidate who is the minimum of m is actually among the first tau. So this is a part of the random order that we did not make any statement about so far. We were only stating, well, who's the one arriving at time t and who are the ones, who's the set of candidates arriving in rounds 1 through t minus 1, but they are still, even in the conditional probability space, they are still in a random order. And because of this, we can now write this just as before. And what you now also observe is that these probabilities here, those simply sum up to 1, of course. This is independent of m, so we are just taking the probability of what is the probability that the set of m, the set of candidates up to time t or before time t is exactly m, and we're taking the sum over all possible different sets, so this is exactly 1, because one of these events will be happening. So what we're getting here is that this is equal to tau over t minus 1. Cool. So what does this tell us? We can now plug this in here. And what are we getting then? We're getting that the probability that we select the best is equal to, take the sum from tau plus 1 to n, and now it is 1 over n times tau over t minus 1. And this is exactly the probability that we claimed. So this is our proof. How does this work? Well, there is this very crucial argument here, and this is what you usually have to understand when you do these kinds of proofs. Actually, there are different proofs to prove exactly this bound. As a matter of fact, we'll see one other proof in the second half of the lecture very soon, but this is one proof that is actually very nice because it can easily be extended, and this is why I wanted to present this here. So, what did we do? We explicitly write down under what circumstances we select the best of the candidates. Now there's the one easy part, namely that the best candidate has to arrive at a certain point. And then there's the other part, that nobody should have been selected up to this point. And if you now close your eyes, then you're maybe not so surprised. I think the only thing that becomes difficult here is getting the exact probabilistic arguments right, but generally the point is somewhat easy, that, well, the best that arrive before time tau, this also has to arrive before or at, the best that arrived before time t. T is the time at which our best candidate arrives. The best candidate, the best one that we saw before that, they should also arrive before or at time tau. And if you then combine these two, then you're actually done. Yeah, as I was saying, what makes this a little complicated to my mind is that, well, now it's not clear who is the one who arrives, who is the best one arriving before time before time t. This could be the second, third, fourth, fifth best overall, but fortunately enough, this is something we don't care about. We only care that whoever was the best up to this point, arrived early enough so that we did not pick them. And in the second part of the lecture, we'll now show that this is actually the best thing that you can do here. Which means that among all algorithms, the best ones are actually these threshold algorithms, which first have a look at the sequence and then afterwards pick the best, the first candidate who is the best so far. The question that we'd like to consider now is there something better than this threshold algorithm? Is there something that gives us a better guarantee? Is there something which selects the highest valued candidate with a higher probability? And the answer is no. Among all possible algorithms, which only use pairwise comparisons, a threshold algorithm is the best one. So the best algorithm will first only observe the sequence and then it will select the first candidate who is the best so far. But as I was saying, this needs one additional assumption, namely that we only use pairwise comparisons. Recall that our algorithm was stating, was actually only using pairwise comparisons. It was because it was stating what is the current candidate and how does it compare to the candidates that we've seen so far? Is it better than the ones that we've seen so far, or is it worse? It doesn't actually look at the values. The way we presented or we understood this original model is that we're seeing the actual values, and it is not clear that now restricting our algorithm to only use pairwise comparisons is actually without loss of generality. But to keep things simple, we'll actually just restrict our attention to algorithms using pairwise comparisons. There's also a theory about algorithms that do actually see the numbers and can make decisions beyond pairwise comparisons. Even then, you can't do anything smarter than here, but this is much more complicated, much more messy. So all we will be showing today is that using pairwise comparisons, you cannot do better than this. So for any n, any algorithm that uses only pairwise comparisons selects the maximum valued candidate with probability at most the maximum of all possible tau, the sum of tau from t from tau plus 1 to n, 1 over n times tau over t minus 1. So I hope you realize that this is exactly the probability that the threshold algorithm, which uses threshold tau, selects the best candidate, as we showed in the first part of this lecture. And now take whatever tau maximizes this quantity. You cannot be any better than this. So actually all we have to show is that the algorithm which maximizes this success probability is actually a threshold algorithm. One thing I might want to say before is that here also we are talking about only the probability of selecting the best candidate. We're not talking about the expected value of the candidate that we're selecting, like this comparison with competitive analysis that I was making. We're only talking about the probability that we select the best candidate, and all we can use is pairwise comparisons. As I was saying, we can get rid of these things, but that's just more messy. So let's keep things simple. Now, actually, the only thing that one has to show is that among all algorithms, there is a threshold algorithm which maximizes the probability of selecting the best element, the best candidate, and this is more or less what we will be doing. But how do we get there? Well, what we'll do is we'll define a suitable Markov decision process, and in this Markov decision process, any algorithm which uses pairwise comparisons actually corresponds to a policy. And then we only have to understand what an optimal policy in this Markov decision process looks like. So how do we define this Markov decision process? Well, what we'll have to do is we'll have to define states appropriately, and well, actions is pretty easy. The actions will be accept and reject. But how do we define the states? What will we have to keep track of? Well, this is indeed the smart thing that we'll have to do so that things become easy. If we decided to do this in a not so smart way, then things would become much more complicated. Trust me, when I wrote the lecture notes, I first thought, okay, this way of writing the Markov decision process is much more intuitive, but then the proof got much more involved. And this is why we are now spending actually more effort in designing a Markov decision process, which might look weird, but eventually in this Markov decision process that we're ending up with, proving or figuring out the optimal policy is quite easy. So what we'll rely on is relative ranks of candidates. What do I mean by relative ranks? The relative rank RT, this will be some integer between 1 and t. This is the relative rank of the candidate arriving in step t. And this is defined how? This is the number of candidates that arrive in steps 1 through t that are at least as good as the candidate arriving at t. What does this mean? This means that if RT is equal to 1, then the number of candidates that arrive in steps 1 through t that are at least as good as the candidate arriving at t, this is only 1. So, how many better candidates arrive before candidate t? Well, 0. So this means that the candidate arriving at time step t is the best so far. Or we could have RT being equal to 2. This means that we see a second best so far. Or we could have RT being equal to t. This means that it is the worst so far because there was nobody, or everybody was at least as good as the one that we saw, that we are seeing now. Or, let's see this also in an example, we might have the following numbers that we first see some candidate of value 18, then 42, then 30, and then 50. And what would be now the relative ranks? The relative ranks would be 1. Well, the first one is always a best so far. The second one is now also a best so far. The third one, well, this is worse than the second one, but better than the first one. So its relative rank will be 2, and the fourth one is again a best so far. Good. Now, why is it helpful to talk about these relative ranks? These relative ranks are, let's first talk about how they are distributed. If we have a uniformly drawn permutation, then we see that RT is drawn from a uniform distribution on 1 through T, and R1 through Rn are independent. Why is this? Well, let's talk about this first property. We are now just considering the candidates that arrive up to time t. And this is kind of the same argument that we used in the first part, namely, among all candidates that arrive by time t, what is the probability that the one arriving at time t is, for example, the best one? It is exactly 1 over t, because any order of the candidates that arrive in the first t steps is equally likely. So we'll see that it is equally likely that this is the best one so far, or it is the second best, or the third best, or it is the worst so far, or whatever we have in between. So all this is equally likely. But what we now have in addition is that these relative ranks are independent. And this is actually something very crucial, because this has to do with how we can reconstruct the uniform, the permutation that we're drawing from the relative ranks. So the relative ranks are in a one-to-one correspondence with permutations, but maybe not in a super clear way. So if we see this sequence here, and if we know that our numbers are, so what the numbers would be here would of course they would of course be in any order, like 50, 42, 30, 18. And now if we go from the back to the front, then we know in which order they appear here. Because from this we see, okay, the 50 is arriving at the last point. So we'll have the 50 at the last point. Now, from this we see, okay, among these, the second best arrives last. This is the 30. So this is why the 30 is arriving here. This is what we can see just going back via these numbers. Now we see, okay, out of the two remaining ones, the better one arrives in step 2, so this will be this 42. And then we'll have the 18, the last one, the last remaining one arriving at in the first step. So R1 through Rn express the permutation. There is a one-to-one correspondence between permutations and relative rank vectors. What is actually surprising about this is that when you're looking at the sequence from the front, then, well, you actually cannot reconstruct the permutation. So when you're looking at this from the back, then you know, okay, the last one in this example will be the best one overall, and so on. But from the front, you don't actually know which of them will be which. But what is actually happening, our algorithm is looking at exactly this kind of a sequence. This is exactly the kind of information that our algorithm has. First, our algorithm, well, just sees one candidate. This will be the best one so far. Then the algorithm sees a second candidate. And the question is, how does this candidate compare to the previous candidates? Is it better or is it worse? In this case, it is better. Now we ask the third candidate, how does it compare to the first and the second candidate that we saw? And in this case, we say, okay, it is the second best among them. And then the fourth candidate, how does this compare to the first three candidates? And then we see, okay, this is again a best so far. So our algorithm knows exactly R1 through RT for the decision in step T, and it selects best candidate overall if it stops at a point T such that RT is equal to 1 and RT plus 1 is greater than 1, and so on up to Rn is greater than 1. So this is indeed a very crucial observation, that we can rewrite the knowledge of the algorithm by time t via these relative ranks. I hope you see that the relative ranks are in one-to-one correspondence with the permutations. So for every permutation we exactly have these relative ranks, and for our relative ranks we have exactly one permutation. As I was saying, look at this from the back. This is how you would get to the permutation. But what the algorithm actually only sees is the relative ranks up to time t. And what is now our goal? Well, we are actually trying to select the best candidate. And when do we select the best candidate? We select the best candidate if and only if we choose to stop or to accept at time t, and at time t we have a best so far, and afterwards there's no more candidate who is best so far, which means all the relative ranks coming afterwards are bigger than 1. But of course we don't know these relative ranks of the candidates who are coming afterwards yet. We definitely know the relative rank of the candidate arriving right now. Let's do some calculations with these relative ranks so that we actually get a little more familiar of how to work with them. Namely, what we'll show is that for all t, we have that the probability that RT plus 1 is greater than 1 up to Rn is greater than 1. This is exactly equal to t over n. Let's first think about this in the way we are used to thinking about random permutations, maybe. What does this mean? That Rt plus 1 through Rn, they are all bigger than 1. This means that in steps t plus 1 through n, no candidate arrives who is better than anything that we've seen up to this point. So what does this mean regarding when does the best candidate have to arrive? The best candidate has to arrive in steps 1 through t. This is exactly equivalent to this statement. And what's the probability for the best candidate to arrive in steps 1 through t? It is exactly given as t over n. But we can also prove this in a different way, which is more in line with what we've now introduced. Well, the probability that all of this happens is, interestingly enough, just the product of the individual probabilities. Why that? Because these relative ranks, they are independent. And now the first one of these probabilities is t over t plus 1 because it is uniformly distributed on 1 plus t on 1 through t plus 1. And then the second one is t plus 1 over t plus 2. This is exactly equal to the probability that we don't see a best so far in step t or t plus 1 or and so on up to the last step. And now what you can see here, what happens is that you can now cancel these things, and what remains is also t over n. Cool. So we now know these relative ranks, and based on these relative ranks, we will now define our Markov decision process, which we will use to prove the theorem. So we define a Markov decision process with the following states. The states will have the form t, rt, c. T, this is the current step. C, or maybe let me first say RT, this is the relative rank at time t. And C, this is our choice so far, and for this we'll have three options, which are called no, best, and lost, meaning that we have. And what do these things mean? Well, no just means that we have no selection so far. Best means we have selected the best so far. And lost means that we have selected a candidate but not the best so far. What are our actions? They are very simple. They are just accept or reject. What are our rewards? Well, in the final step, we have a reward of 1 if the best candidate has been selected. And other than that, we have no rewards. And our starting state is now that we are starting in the first step. We've seen the best candidate so far, and we haven't selected anything. Now I won't write down all the transition matrices. I think this is something that you can do on your own if you want to understand this in more detail. But what is it that is happening now? Actually, we're keeping track of not too many things. We're keeping track of only the current step, the current relative rank, and if we have selected something, and whether this was good so far or not. And now what happens is that we have these steps that take place, and in each step we say either we accept or reject the candidate based on the current relative rank. And now what the MDP can do is first of all, will keep track of our decision, of course, in this last part of the state. Of course, it might happen that then we are moving from a certain state to where we had the best so far, that then a new best so far arrives, which means that the new relative rank is 1. And in this case, this is moved from best to lost. And moving from no to, best, this is only happening when we're making an accept decision. It might, of course, be that we're moving from no to lost if we accept a candidate which isn't even the best so far. So then we will immediately have lost, in the sense that we've selected a candidate which is not best so far, which of course cannot be the best overall. Let's see this maybe again in our example from before, with concrete numbers. Our values there were 18, 42, 30, 50. And what are now our states? Well, we'll now transition through the following states. Let me first only write down what our policy or algorithm has no control of. This is the first component, the first two components of the state. This will look like this. So we'll only count up the step number in the first component, and in the second component we'll keep track of the relative rank. So the relative rank on here is of course 1, then the relative rank is again 1, then the relative rank here of the 30 was 2, and the relative rank of the 50 was 1 again. And let's now say that we accept the second candidate, just for concreteness, then what will our states be like? First, we haven't selected anybody. Then we're moving to a state where, why does it still say no here? Because then we are actually presented this state where we haven't selected anybody, and then we can choose to select this candidate. And in this case, I was saying, yes, we do accept this candidate. So then we're moving to this state where we've selected the best candidate so far. And then what happens here is that, well, we've still selected a candidate, but now a better candidate arrives. So unfortunately, then we have lost. So this is the state sequence that we would be seeing. And what's our reward? Our reward is simply 0, because we are not accepting the best candidate, which doesn't surprise because we're only accepting the 42 and not the 50. Good. So this maybe feels a little difficult at first sight why we're using these kinds of states. But the advantage is that we actually now have only very few states. We only have like these 3 components, yet the history of the states actually, when we look at all of this together, we can, well, infer what happened. We can actually see, okay, this was the permutation that was happening, and also we can see how did the algorithm decide. And also, the final state is actually enough for the decision whether we selected the best candidate or not. So we can just define the reward of 1 because we know that now this algorithm has to have selected the best candidate. So the amazing thing is that we now only have to understand the expected reward that we're getting with an optimal policy starting from this state, and fortunately enough, we can just compute the optimal policy for this Markov decision process, and it turns out this is not super complicated. Why is this? Well, what we're interested in is things like this. So what is the expected reward that we're getting from the state TRTC? By the way, we ignore the time horizon here, just because this this is clear from the context. So what is the expected reward that you're getting from such a state? It is time t, the current relative rank is RT, and your current decision is C. Well, let's talk about the very easy case. You've lost. You've selected somebody, but this somebody didn't turn out to be the best one because a better one arrived afterwards. Well, then of course the expected reward will be 0. Let's now consider the case that we've selected a best so far. Well, then there's not much we can do anymore, and we can only hope that nobody who's better arrives in later rounds. which meant that all of these relative ranks should be bigger than 1. In both cases, it doesn't actually matter which action we choose because we have already committed to one of the candidates. Now let's talk about the case that we have not selected anybody. And let's talk about the case, which is actually the most interesting case, that the best candidate so far arrives. Well, what is now the expected reward that we're getting from such a state? It is clearly the maximum of what we can get by the 2 actions that we can choose. What are the 2 actions? There's the one action that we accept, then we'll be winning with the probability, or our expected reward will exactly be the probability that that no better candidate arrives. So this part here corresponds to the accept decision. And then there's the other action that we have, which is the following. Now then we are moving to a random other step, and from this point onward we'll see what will happen when we haven't selected anything. This is exactly what is happening when we reject. This looks a little different from how we wrote this earlier when we were talking about Markov decision processes, because we wrote this out by the sum times the probabilities. This we are now just expressing by the expectation, because this keeps our life simpler. What about the immediate reward that we're getting? There is no immediate reward, so this is only what is coming, the potential reward that is coming in the future, and we're choosing the action which gives us the higher of the 2 expected rewards. Now there's the other case, that the currently arrived candidate is not a best so far. Then technically we could also decide to accept this candidate, but then we would have lost immediately. So we see all we can do is we can reject this candidate, and then we'll just move again to a random state and follow the optimal policy from that point onward. Again, we remain in a state where we haven't accepted anything. Good. Now, let's now write PT for the expectation of this term that we were talking about last. So now we'll draw one of these ranks here also uniformly at random, which will be in the from the set 1 through t. Now, how big is PT? Well, fortunately enough, we only have to use these equations. Namely, PT, this is the expectation of RT, V star RT, comma, no. This now means that with probability 1 over t, or probably, yes, I'm getting ahead of myself here, with if now RT is bigger than 1, then what we're getting here is exactly PT plus 1. Or what else might happen is that the rank is exactly equal to 1. And in this case, we're getting here the maximum of these two statements. And we see that the second part in this maximum is again PT plus 1. So what are these probabilities here? This probability is t minus 1 over t, whereas this probability is 1 over t. And this probability here is equal to t over n. This is something that we figured out earlier. Now what does this mean? This pt is now equal to t minus 1 over t plus 1 over t times the maximum of t over n and pt plus 1. And also here we have a pt plus 1. And now we have a recursive formula for the pt, which we can solve. Why can we solve this? Okay, this maximum operator, this actually looks a bit annoying. But what you can see here is that pt will always be at least pt plus 1. Why is this? Because here you're getting t minus 1 over t times pt plus 1, and here you're getting something that is only bigger than pt plus 1 times 1 over t. And at the same time, what we also see is that t over n is smaller than t plus 1 over n. And what does this mean? This means that if pt plus 1 is less than t over n, then pt plus 2 will definitely also be less than t plus 1 over n. And this tells us something about this, what we're getting here as the maximum. This now means that pt will have to have the following form. It will be like t minus 1 divided by t times pt plus 1 plus 1 over t times pt plus 1 for tau being smaller than a certain t, and afterwards it will be t over n, what gives us the maximum of the two here. Because once we have the maximum, we'll keep having the maximum. So once the maximum turns out to be t over n here and not pt plus 1, then also in the following step it will turn out that t plus 1 will be bigger than pt plus 2, and so this is why first in this recursion we'll always use this part, and then in this recursion we'll always use this part. For small t we're using this for the recursion, for large t we're using this for the recursion. And this is true for some tau, of course. There will have to be this point in between where we're switching. And this now means that this pt is equal to pt plus 1 for t being at most tau, and afterwards it will be t minus 1 over t times pt plus 1 plus 1 over n for these larger t. Good. So if you now look at this carefully, what you realize is actually the optimal policy has to be a threshold policy. It has to use some threshold before which we are rejecting and after which we are accepting if the relative rank is 1. If the relative rank is different from 1, we'll definitely reject anyways. This is something that you can actually already see here, and so we are actually already done. But given that we now have this formula, we can even figure out what are the values of pt, and we can simply solve this recursion. And how big is p1? p1 will be the same as p2, will be the same as, and so on up to p tau plus 1. And how big is p tau plus 1? It is 1 over n plus tau over tau plus 1 times p tau plus 2. And how big is p tau plus 2? It is 1 over n plus tau plus 1 over tau plus 2 times p tau plus 3. And so on. And if you now follow these steps, then you'll see, okay, this will be the sum of tau plus 1 through n, 1 over n times tau over t minus 1. And this is exactly the kind of statement that the kind of equation that we had. And the one thing that you should notice is, of course, that P1, what was this? This was V star of 1, 1, no. So this is the expected reward of an optimal policy starting from our initial state. Good. So getting the math right here at the end, this is a little ugly, but it's actually not difficult. One of the difficulties is figuring out this up here, namely that we have, or what I think is maybe the most surprising step, is that here you have this monotonicity properties. And this is why you can simplify this part down here, that you say, okay, first I will always use this part in the max, and then I will always use that part in the max. And this is exactly the reason why there is this tau at which we're switching from one to the other. And this is precisely the reason why a threshold policy is optimal in this case, which corresponds to exactly the kind of algorithm that we were discussing in the first part of today's lecture. Good. So this means we are done now, because we've shown that not only threshold policies are optimal, but also you can also understand as a different proof of how to bound the probability that the best element is selected by the threshold policy, namely it is exactly this sum, and as I was saying, this sum will always be, for the best tau, at least 1 over e. Figuring out the exact numbers is a little more difficult. I think there is no closed formula for this. It is always at least 1 over e, but for n equals 1, for example, the probability that you select the best is of course 1, because there's only one candidate that is presented to you and you should select it. You could now figure out what it is for 2, for example. For n equals 2, then what will it be? I guess, oh, that's now even not so clear. Do you want to accept or reject the first candidate? Well, this is something that you might figure out yourselves. But generally, we have this recursion formula to actually get the optimal guarantee for any n. Oh, now I realize what you'll do is you'll just accept the first candidate, or you'll accept the second candidate. This gives you a probability of 1/2, and that's the best thing that you can do in the case of n equals 2. Now what you can do is figure out what you should do for n equals 3. Where should you stop? Probably you should have a look at the first one and then decide for the second and the third, and this will give you some success probability, which you're finding out with this formula. So this is it for today. I hope you enjoyed today's lecture. Please do reach out to me if you have any questions, and as usual, stay safe in the meantime I see you in the next lecture. Bye.